everyone. Today we are going to discuss a very interesting model with its creator. Before we dive into our questions, could you please briefly introduce yourself?
Sure. So I am Aniruddha Belsare. I am an assistant professor of disease ecology at Auburn University College of Forestry, Wildlife and Environment. I am a disease ecologist and a disease model.
My first question is could you please explain the main purpose of this model?
Sure. So this model simulates the multi-host, multi-serovar dynamics of Leptospira. Leptospirosis is a neglected disease. It's a huge public health issue. This disease disproportionately affects impoverished community, but it's not just limited to the developing world. Recently, New York City has reported an increased number of cases of leptospirosis in people living there. So it's a global issue. And one of the main reasons we came up with this, we thought of this model is because all the current control measures so far have been uniformly ineffective in addressing this public health threat. So with this model, we wanted to put forth a tool that can be used by public health people to design locally relevant and effective disease control strategies.
So moving on, let's talk about the development process of this model. Uh, what were the main challenges in the developing this model and the development process?
Yeah, I think one of the issues we struggled with and still struggle with is what level of detail needs to be incorporated in this modeling, in the model or in the modeling approach. I think it goes back to those issues discussed by Levins in the late 1960s about, the trade-off between generality, realism, and precision. So that was one of the main issues, like how do we scale this model so that uh, uh, the main purpose being we want people across the world to use this modeling tool to make better decisions. And so it has to be accessible. It also has to be relevant. So the model needs to be adaptable, customizable, and all of that. So that was where the main struggle was. I also think this complexity and this complex modeling approach comes with another issue, which is communicating this complexity and kind of if you want people to use it, then it also is important that you have to train them in aspects like attention to detail, because the model, the way it is, the way even the interface with NetLogo is so user friendly, it's very easy to set it up in a way so that the model breaks down, or so that the user puts in conditions without realizing, and the result into some spurious results. So I think these are the two main challenges, given that we want to have this as a tool to be used by public health personnel.
So now let's discuss the results of this model. What are the main insights coming out of the model analysis?
What we have so far done with the model is um, we have done virtual simulations with interventions that are kind of, you know idealistic, but we have also tested interventions that are more on the real world side of the things. With all of this, what we did was interrogated or explored or investigated the disease dynamics in this multi-host, multi-serovar system. So very briefly, the model represents the real world complexity in the sense that we have a host community. We have multiple species of hosts, including humans, who can get the disease. And then we have in the model host adapted serovars of Leptospira. Now, the complexity arises when these serovars adapted to a particular host also infect other hosts, and the host response is not uniform. Sometimes there is some in some cases they will develop lifelong immunity. In some cases it will be like a limited term immunity, and so on and so forth. So what we were able to get out of these model runs is some very important lessons, I would say, in terms of informing disease control. So we tested the model with rodents, dogs, and humans as the hosts, and with a rodent adapted Leptospira serovar and a dog adapted Leptospira serovar. Very briefly, what we found was that rodents were the main contributors of leptospires for both serovars. So, what happens is an infected animal excretes leptospires, which are the infectious agents, into the environment via their urine. So urine is what contaminates the environment, and humans get the infection from these contaminated environments. So who is contributing to the environment? And with the rodent realistic rodent population and the realistic dog population, also keeping in mind that the volume of urine excreted per day by a rodent and per day by a dog, and if they are infected, they put out different quantities of leptospires per ml of urine that they excrete. And so looking at all of this, what we found was that rodents were the main contributors, no matter which strain it is. Then rodents independently sustain circulation of the dog adapted serovar as well. So this has important implications for designing management strategies, right? It's not just vaccinate dogs and you will get rid of the dog serovar. In that case, rodents actually, even if you eliminate the leptospirosis from the dog population, there is a possibility that rodents would still keep on passing out the dog serovar for a while. And then dogs played an important role in distributing the rodent serovar in the landscape. So there are lots of insights which could really help design an informed disease management strategy rather than blanket strategies like rodent control, dog vaccination, dog control. So that's the gist of what we have found so far.
It can be very interesting and helpful for public health management, I believe.
Right.
So my next question is about ComSys.net. You have archived your model on the ComSys.net. So what do you think about making the models available to other researchers, specifically in the area of public health management?
Right. I believe in, open science practices and transparency, reproducibility, and all of that. So ComSys provides that opportunity to make your models accessible. I also think, and maybe others have talked about this, but one of the key issues I really subscribe to, and I really want to talk about this with other modelers, given an opportunity. I think models should be immortal. We should try and make models immortal. That is not just limited for a thesis chapter. Because a lot of effort goes into making these models simulate complex systems. And there is no reason why scientists, researchers, modelers would have to reinvent the wheel every time somebody thinks of a complex system. So if you want to make them models immortal, if you want to have a wide applicability, wide use of the models that you develop, they have to be transparent, they have to be accessible to the users. And I think that's what ComSys provides an opportunity with, the peer review of model code, with certification of that, peer review of that, verification of the model, and all those things. So I think making it available is an important step if you really want to reach out and have the model used by a wider audience.
So finally, looking ahead, what's next with this topic? Are there follow-up studies available or planned based on this model?
Yes, we are continuing the work, and as I said, there is a lot of possibility of applying this model to the real world situations, making this more adaptable, to make it more locally relevant. And so, one of the um, the directions that we are taking right now is to combine it with field studies, so that the models can be better parameterized and be more relevant to regions where leptospirosis is an issue. We are also developing collaborations in areas like real-time detection of leptospirosis, which will help us in the process of uh, model validation in some sense. So,
Thank you. Thank you very much for joining me.
thank you.